Okay, I'd like to go through the Marcq and Hilaire example that's in your book. 2nd of October at 14:29, we're given our DR position and we took an altitude with the sextant of the sun's lower limb and it read 28 degrees 05.0. The index error is 2 minutes on the arc, height of eye 6 metres, and our chronometer reading is 5 hours 31:13 with an error of 2 minutes 30. First thing that you do is to calculate the GMT. So we write down our apparent local time, which we've been given, 14:29 on the second, and we apply our longitude to that time. So we convert 45 degrees 20, which is 3 hours 1 minute, west. Now if it's west, Greenwich is best. Therefore our GMT is the second 17:30. So we now look at our chronometer and we see we've got 5 hours 31:13. So our time must be 12 hours plus the 5, 17:31:13, and then the error. So we write down our chronometer reading now as 17:31:13, not the 5, because our time here is 17. Error 2 minutes 30, so we have a GMT reading of 17:28:43, obviously subtract that. Now we use the GMT to obtain our GHA and our declination. Okay, so that's the second stage. First of all, get your GMT, then use the GMT in the tables. So we go to the 2nd of October, and we go to our time at 17 hours, and we get our GHA of the sun plus the declination, and check which way the declination's going. You can see it's increasing there. And then we apply the increments. So we go in at 28 minutes 43 seconds, and we apply the increments to the declination and the GHA, and we had the D was 1.0. Now we've got our GHA and our declination for the vessel. Okay, we then apply our westerly longitude to the GHA, and that will give us the LHA for the sun. Longitude west, Greenwich is best, so we subtract. So now we've got our LHA and our declination. We then turn our attention, the third phase, to our sextant altitude. We know it's 28 degrees 05, we're given that. The first thing that we apply is our index error. If it's on the arc, we subtract it. So on, we take it off. That gives us our observed altitude. Apply the dip, which is our height of eye, and that gives us our apparent altitude. We get the correction for dip using a height of eye of 6 metres from the tables. That gives us our apparent altitude. Then we go into the tables using the sun's lower limb and the month of October and our altitude to get the main correction, and that's 14.5 minutes. So our true altitude is 28 degrees 13.2 minutes. That's a true altitude. Always subtract that from 90. And that will give you the true zenith distance, which is 61 degrees 46.8. So that the first three phases: get the GMT, get the LHA of the sun and the declination using the GMT, and then go through the sextant altitude to get your true altitude. Now the next phase, we use the formula. Cosine of the calculated zenith distance, cos LHA times cos lat cos dec, plus or minus sine lat times sine dec. We use minus because the latitude and declination are named differently. If latitude and declination were both north or both south, we'd use plus. So we put those into the formula. Be careful when you're doing this, because where we've got this plus or minus here, you have to actually group this as one calculation. Sine 4730 times sine 346, that's one calculation, minus this other full calculation. And you'll find that it comes to 61 degrees 49.8. So that's our calculated zenith distance. So we bring forward the true zenith distance that we got from our sextant altitude, 61:46.8, and we find the difference between the two is 3 minutes, and that is our intercept. It's towards, because true, tiny, towards. The true value is less than the calculated, therefore the intercept is plotted towards. Just on a note there, if you use sine, CZD, sine, instead of cos, then you'd have got the true altitude out. So from the previous calculation, our true altitude 2813.2, by using sine, you'd have got the calculated altitude. Okay, the calculated altitude, which you would apply to the true, and that would give you the intercept the same. So now that we've got our intercept 3 towards, we need to know what angle to set it at, what azimuth. So we use our LHA, latitude and declination, the ABC tables, which we've done an example of already, to get our azimuth. So we get the A value at 1.32, now that's south, as per the tables. B, 0.10 south, obviously because our declination is south. So that gives us a C value of 1.42 south. And when we look that up in the tables, it's 46.2 degrees. Now it's southwest, and it's west because the LHA is less than 180 degrees. So we go southwest, so it's 180 degrees plus the 46.2, and it gives us a bearing of 226.2 degrees. So what we actually do, if that was your DR position here, north, south, west and east, we'd draw from the DR position a line at 226.2 degrees, and we'd measure 3 miles on the scale that we're using, and then we'd draw 90 degrees to that, our position line. So our position line is 136.2 degrees, 316.2. So it's 90 degrees to the bearing. So on your graph paper that you're plotting, you need to work out how to get your position. Now in the book, you've got the drawing in there, and you've got your DLAT and your departure. So it's 226.2, 3 towards. We need to know how to, well, we read those off on our scale, so we know what our DLAT is. We've got our departure, so we need to calculate our D long. So what we do, we use departure is D long times cos mean lat, which is the plain sailing formula. So D long will be departure divided by cos mean lat. The departure that we measured on the scale is 2.2. Cosine of 47.48, which is our mean latitude, and that gives us a value of 3.2. So that's our D long. So from the plot, our D lat is 2.1, and that's south. So when we put our D lat in, we're going from the DR position, we're going southerly, and so that our D lat will be southerly, and our D long is going to be westerly because it's a southwest. The azimuth told us we were southwest. Therefore, we're going to use south for the D lat and D long 3.2 west. So when we look at our DR position, because it's 2.1 south, we subtract it to get our latitude, and then we've got our D long there. Because we're going westerly and we're already on a westerly longitude, obviously we'd add that. So that's how you would solve the Marcq and Hilaire problem with a sight.